there. It's always nicer to interact in that way. And I very fondly remember visiting Istanbul, actually visiting my friend Onur Pusuluk, and we have been collaborating for a long time. And I hope that after this crisis is over, there will be many more opportunities to meet directly. So what I would like to say is a number of brief statements about the fundamental problems in quantum gravity. And in fact, let me put this first slide on. What I will proceed to tell you is that in my view, most of these problems that are discussed are not really problems. Or maybe I should put it differently. They are no different to the problems that we encounter in any other field theory when it's applied, for instance, to the electromagnetic field. So I will give a sequence of kind of negative statements. I'm very fond of these early priests from Cappadocia, I think in Turkey, which invented this way called via negativa, I think that you may know, which is a philosophy that is meant to reach an understanding of God by denying things that God is not. So I think here I will also approach quantum gravity in a similar way, that I will tell you what the problem is not. And then hopefully whatever remains might actually be a problem with that. So frequently you will hear that people talk about entanglement being an issue, because entanglement is a kind of correlation that doesn't exist in classical physics. And people frequently say that's why it's difficult to quantize gravity. Then another obvious culprit is the equivalence principle, which in this case comes from general relativity. But of course, we have to somehow reconcile this with the superposition principle. So the question, as always, is we have very strong principles on both quantum side of things and gravitational side of things. And the question is, could they all be put together without breaking either of these theories? And of course, we don't know. But there are many issues that you will read about. And it seems to me when you look into them a bit more closely, they are not really any different to other issues we are actually facing in many other directions. And so I listed kind of a number of them that follow, and I will go through them briefly. You know, the question of observables, the question of time, the question of nonlinearities, and all of these things. So I'm going to go in the first part through that. And then what I want to say really is that there is a real problem out there. And the problem, of course, is the weakness of the gravitational field, that it's extremely hard to experimentally reach a regime where both quantum and gravity matter. That's the problem, really. And you know, there's this famous physics cube where you have the three axes which are governed by the three, as we think, are fundamental constants. You have G, you have C. It was more convenient to write 1 divided by the speed of light, and you have h bar here. And of course, when C goes to infinity and h bar goes to 0 and G goes to 0, we are in the at the origin of this coordinate frame, and that's the usual Newtonian classical mechanics. And then you can see that as far as gravity and quantum mechanics, we have barely explored the top right-hand corner, which you can call under different names. Some people would say that's non-relativistic in quantum, in the sense that you don't worry about the speed. The speed is small compared to the speed of light, but somehow gravity and quantum both matter in this regime. Another theory that frequently comes here is the semi-classical gravity, which is the theory where you say, let's quantize matter, but let's not worry about gravity. Let's think about gravity as a classical field. And this is something that is very difficult to do consistently. In fact, I will argue against it in a few slides' time. But my point here is that we have a few experiments in this corner, but we haven't explored at all much more than that. We haven't gone beyond this zeroth order if you like, approximation in quantum gravity. And what's exciting and what I want to communicate at the end of the talk is that we are approaching very, very rapidly now the time when actually we could experimentally say something meaningful. And I would like to convince you of the fact that at least some aspects of gravity have got to be quantum. I think we have pretty good arguments in some regime that there is nothing else to do for us really but quantize at least some aspects of gravity. Of course, it would be great to test this, and I think that's the experiment I want to finish with. But I think, like I said, the time is great now for physics because our technology has finally caught up with many of these ideas. Some of them are, they go back 50, 60, 70 years actually, but no one knew what to do with them really. So let me go through some of these issues as people flag them up. You might open a paper and which says entanglement is a non-local effect, and gravity is meant to be a local field theory, and therefore we have a problem. And what I want to say is that this is not a problem. This is a grammatical, so to speak, mistake, because the non-locality in quantum mechanics is a very different kind of non-locality. It's what we call Bell non-locality to the non-locality that you would get in the standard field theory, where you may be thinking of something propagating faster than the speed of light. So in quantum mechanics, entanglement has a perfectly local description. It's just harder to see if you're working in the Schrödinger picture. And sometimes Schrödinger picture gives us some kind of mistaken feeling that there is something genuinely non-local in quantum mechanics. But as most of you know, in ordinary quantum field theory, quantum mechanics is perfectly compatible with microcausality and locality principles. It does not violate anything coming from special relativity. So the reason why in quantum mechanics we use the word non-locality is because Bell gave us a choice. Bell said either you have to lose locality or you have to lose reality. What he meant by reality is that everything in the universe is described by numbers, which can be assigned to every point in space and every instant in time. This is something we would call a local hidden variable. And in fact, as you know, Bell's inequalities, and they've been now closed beyond reasonable doubt, tell us that we can't have both realistic description and local description. And I think most of the people, most of my colleagues, would actually opt to keep locality, if you like. They would say, oh, locality is certainly never been violated in any experiment. But what we must do to acknowledge all of these experiments is that reality cannot be based on numbers. Reality must be based on operators. These are the Q numbers, as I call them. So basically, that's what it means to properly do quantum mechanics in a local way. It means we should acknowledge that everything consists of really observables. So every point in space has a bunch of quantum numbers assigned to it, and that's all there is to it. And if you do quantum physics this way, this is a very quick example, actually. I've written a couple of papers on this issue. It's just a standard interferometer where a photon goes through the first beam splitter, acquires a phase, and notice the phase is acquired locally in one of the arms of the interferometer and not in the other one. And then you have another beam splitter and you do your measurements and you can estimate the phase. This is a standard Mach-Zehnder interferometer that probably serves as the best example of what we would call a quantum bit of information. Now, if you use the Schrödinger picture, and 0 and 1 are simply the vacuum state and the one photon state. So 0 means the photon is not in one of these branches, and and one means it's in the other branch, and vice versa. So after the beam splitter, you can actually think of this state of a single photon in a superposition as an entangled state. And now the problem with the Schrödinger, the problem that with the fact that we are only now talking about states and not about observables, we're kind of ignoring half of quantum mechanics. The problem is that if you want to insert a phase into this state, then the phase can either come from the one arm of the interferometer, the other arm of the interferometer. It could be with a plus sign or a minus sign, and you simply will not be able to tell. This experiment here, unless you tell me where you put the phase shift, this experiment is incapable of telling you. And sometimes some people make a mistake to think that this means that the phase is non-local. It's not. The phase is really kicked into one of the arms locally, and it does not exist, so to speak, in the other arm. But the Schrödinger picture, if you only look at the wave function, gives us the wrong impression. There's nothing wrong with the Schrödinger picture. It just gives us the wrong impression that somehow the phase is non-local. And in fact, the way to deal with this is the Heisenberg picture. And of course, that's what every field theorist would do, because our wave function in the field theory becomes a field. And I don't want to bore you with all of these details, but if you describe the electric field, these are the creation and annihilation operators. Electric field in the left branch, in the left arm, electric field in the right arm. Here is the phase kick. And you can see that when it comes to operators, now I'm involving the operators instead of the states, you can clearly see that the phase is kicked in the left arm of the interferometer, not the right arm. It's very clear where the phase is. It's not non-local. It is wrong to put this phase on the other side. That's not what the experiment has done. And actually, if you go through the second beam splitter and all of that, like I said, it's a very simple calculation. You will get exactly the same probabilities. Of course, this is exactly the Heisenberg picture calculation, but everything you do will be as local as in any other field theory. In fact, Maxwell's equations would predict exactly the same. The only difference, like I said, is that the electric and the magnetic field become operators in quantum mechanics. They cannot be numbers. It's inconsistent to think of them as mere numbers. We have to upgrade them into operators and acknowledge that they don't commute and so on. So the same, incidentally, I know this point is even more controversial sometimes, but the same goes for any other thing that people claim is non-local. Another famous example is the Aharonov bomb effect, where you have an electron undergoing an interference, which splits at some point, and it encircles a magnetic field, which is confined only to one point here. And then when you measure the interference fringes, you actually realize that the field, which is zero everywhere other than at a very small point where you can confine it to a very small area, somehow, even though the electron never directly interacts with the field, it seems that the interference fringes do depend on the flux of this field. So it's exactly the B field times the area. And sometimes people say this is clearly non-local. The electron can feel these fields at a distance. And this is a very similar mistake to the previous one, because there is nothing non-local here. In fact, I think if you look at the paper that I'm recommending here by Chiara Maletto and myself recently, what we gave is a fully local description of the whole experiment, where the electron at each point couples to the local electromagnetic field. That signal travels to the flux, couples to the flux, and then travels back to imprint the phase into the electron. So I can tell you a story, providing I quantize everything. The key thing here is that the field must be quantum. If you keep the field classical, you cannot explain the Aharonov bomb effect. And the simple reason for that is that the classical field doesn't understand what it should do when a charge, which is a source for the field, is in two places at the same time. The classical field doesn't have the description that corresponds to the charges being in a superposition of states. That's the whole point of quantizing fields. That's why we must quantize them. So basically, providing you quantize the electromagnetic field, then this description of the experiment is as local as anything else we do. Now let me move briefly into a few other problems to set the scene actually for what, in fact, all of these things I'm communicating them as problems that some people would say they are problems. I claim, in fact, not only are they not problems, but they are exactly the opportunities where we should look into them more in more detail in order to see and to design experiments that test exactly the issues that we are discussing now. So the equivalence principle was the second thing that I said, and frequently there are papers saying that the equivalence principle is violated quantum mechanically, and I will claim it's not. And it's a very simple issue because one of the versions of the equivalent principle says that gravity and acceleration cannot be locally discriminated. So at a single point in a very small region around a given point, if you're feeling a gravitational field, it should be exactly the same as far as all physical consequences are concerned to the situation where there is no gravitational field, but you are being accelerated with the acceleration that's equal exactly to the g, to the gravitational field. And now you have a question immediately. What if a massive object is in a superposition of two locations? This is exactly the key question in quantum gravity. The same way as the key question in electrodynamics is what happens when I put a charge in a superposition of two different locations? And we know what happens there. Now, I'm going to claim that the same thing ought to happen with gravity. So here is a very simple illustration of this thing. I have a massive object which is superposed across two places. And I have a test object which now has to decide which way it ought to move. And you will have various predictions there. My colleague Roger Penrose would tell you that at this point, quantum mechanics collapses. And the test object has to decide whether to accelerate towards one of these locations or the other location. And this would be the case if the equivalence principle could not be upgraded to quantum mechanics. If you really stick and insist on the fact that it's only classical, then of course you must somehow destroy the quantum effects. But that's not what we do in electrodynamics. We do the exact opposite. And this is what I'm predicting would happen in this experiment. And we are almost there. We almost know that this, I think, will happen. What this test mass will do is accelerate simultaneously towards both of these locations. In other words, it's going to entangle itself to this. So if gravity is quantum, a massive object in a superposition produces simultaneously two different gravitational fields at this point. One pulls this way, the other one pulls that way, and quantum mechanically, both of these will happen simultaneously. And what I'm saying now is nothing other than the Schrödinger cat experiment. I think most of you will know that every experiment in quantum mechanics is actually Schrödinger. There's no other experiment. This is the experiment. The only difference, of course, is that some of these experiments can be more and more complicated. Even making a quantum computer is the same as Schrödinger's cat. It's just that making a large quantum computer is, of course, extremely challenging. So the statement here, and I like this word totalitarian. I learned it from David Deutsch, who learned it, I think, from Bryce DeWitt. Bryce DeWitt, I think, had very similar views that gravity must be quantum and must be quantized. And he had his own way of doing this. But this was, like I said, 70, 80 years ago. And it's a shame he hadn't quite lived this long, because I think he'd be very excited to see what we could actually now do experimentally. So the claim here is that whenever a superposition of any kind couples to anything else, then that other thing must become part of this superposition. And that's exactly what Schrödinger says. Whenever you look at a particle that could be emitted and not emitted at the same time, you are going to join the superposition by seeing in one branch no emission and in the other branch an emission. And this is the only way to think consistently about quantum mechanics. Now, of course, we haven't tested this in really macroscopic domains, and I'm not claiming that I know what's going to happen there. Maybe it won't happen like that. But it seems to me that at this very low level, which is almost accessible, things will go this way. They are not going to be any different to what we've seen with other fields. And that's really the main claim. I don't want to bore you with some other phases that could be observed there as well. I'm going to skip this because it's all really related to variations of the equivalence principle, and can I test all of the effects, the classical effects and so on in the quantum domain. And I think they will reappear briefly later, which is why I'm skipping them now. Here is something that could possibly be a different problem, but it seems to me not. And again, you will probably be able to read many papers along these lines. People say, when I talk about the electromagnetic field, then I assign the operators for the electric and the magnetic field to every point in space and every instant in time. But now we've got a weird, with gravity, of course, gravity, the whole point of gravity is that Einstein got rid of gravity. Gravity actually does not exist really in general relativity, but what exists is the curvature of space-time. The g mu nu, the metric, is actually not only the gravitational field, but it's also the underlying space-time. And some people say this is weird because now I have to talk about g mu nu as a field expressed on the space-time, which is g mu nu itself. Some people say it's a field on itself. What does that even mean? And again, I'm not pretending that I know what this means, but in other field theories, quantum field theories, it is perfectly legitimate to express one field as a function of another field. This is not a problem at all. In fact, I could even take the gravitational field and express it in terms of the electromagnetic field, which will serve as my underlying space, if you like, for different values. So I can say the value of the gravitational field is 10 meters per second squared, the acceleration, at the point when I've got 10 photons in the electromagnetic field. So I can always do this in a relational way. There's nothing weird about it. We do it all the time, actually. Coordinates are really just arbitrary. The only interesting thing here, so I don't think this is, necessarily a problem. There are mathematical issues there, because if you now want to start doing differentials, if you don't want to do d by dx of your g mu nu, what you're doing now is really taking a derivative of an operator with respect to another operator. And this to me sounds like an interesting mathematical question. I think people who are trying to quantize geometry worry a lot about this, and I don't even know how to begin to tell you what this would mean. So I have no idea. And I don't even know whether this is something that we need to be doing, but it's an interesting question. And then, of course, for us physicists, the interesting question is, should we quantize both the first g mu nu, the field, as well as the underlying g mu nu as space-time? So some people say maybe quantizing space-time is not the same as quantizing gravity. Maybe these two will lead to two different things. Maybe we need to do both and all of these questions. I have no idea what the answer to this is, but in the regime I'll be telling you about, where I think nothing unusual happens, none of these issues actually arise. So I don't necessarily see a problem. I'm not saying that there won't be a problem, but it's quite interesting actually that I don't think there is a problem there. And this leads me to another related issue which you may have read about, which are quantum references. So as soon as you acknowledge that g mu nu could be quantized, that means you're talking about a universe where you can have a superposition of two different geometries. And the question is, what does that even mean? And my answer to that would be very similar to the equivalence principle in quantum mechanics, which is simply to say that a particle that encounters a region where there may be a superposition of two different spacetimes will simply, in a linear fashion in this regime, respond to both of these spacetimes. So there will be a branch in which the particle follows a geodesic according to one metric, and equally superposed with this will be a branch in which the particle follows the geometry of the other metric. And this is exactly what, if we could wake Schrödinger up now from the dead and we could ask him this question, I bet you that he would say exactly the same thing. What else could it be, is the statement. Of course, we don't know. And the exciting thing for all of us is that maybe something different happens. And that's what's interesting. But I just want to alert you to one fact. This is a slide from a popular talk that I didn't want to change, actually, which is why it looks a bit like a cartoon comic for children. But the point I'm making here is that in quantum mechanics, the way we describe observers and the observed is through a sequence of nested scenarios in which each of these observers at a higher level couples to everyone at the lower level and gets affected by every observer at a higher level. And actually, quantum mechanics gives us some very counterintuitive predictions there. Again, I wrote a lot about it in these two papers, and please have a look at them if you want to know more. But what I want to say is that there is no inconsistency between different observers seeing different things at the same time. This simply is exactly the consequence of quantum mechanics. This is not something that goes against other bits of physics. It simply is what it means to be fully quantum mechanical. So here I have a photon that interacts, Schrodinger's cat experiment, where the photon in one branch kills the cat. It doesn't kill the cat in the other branch. Then I have Bob, who is the observer inside the laboratory. And Bob himself gets entangled, like I said. In one branch, Bob sees a living cat. In the other one, he's very sad and he sees a dead cat. Now there is Alice outside of the whole thing. And of course, Alice has her own story. She doesn't know which of these two options Bob is in. What she does know is that Bob is in a superposition. He's in an entangled state of the whole. Of course, this is assuming that quantum mechanics does not break down anywhere. This is simply assuming the formalism that it applies to this. And so these nested observers, the next observer is the Mad Hatter, from Alice in Wonderland. So there's Alice and Bob and Mad Hatter. And Mad Hatter is controlling what Alice does, interacts with Alice, and so on. So this is a scenario that some people call Wigner's friend. But what Wigner imagined was much narrower than actually what quantum mechanics allows us. And that's where it gets interesting, because Alice, for instance, if she has enough experimental power, can in fact re-interfere these two possibilities and bring them back into one and the same universe, so to speak. So Alice, even though Bob feels like in each branch he's made a definitive observation, what Alice is capable of doing is actually making an interference experiment. If she can do that, it's extremely challenging, but as a thought experiment. And actually, she can, despite the fact that Bob has made an observation, still interfere these two observations. So it's very interesting. And the same story now goes for different metrics, in the sense that each of these Bobs could see a different G mu nu. Alice herself could exist in yet another G mu nu outside of that, and none of this is a contradiction. Quantum mechanics beautifully accounts, in a weird way, it's counterintuitive, of course, compared to classical, but there is no contradiction. That's kind of the bottom line I want to make. And maybe this last question, which is what people call the problem of time, because you really want to quantize the whole universe. You're talking about gravity at the level of the whole universe, and now you want to merge it with quantum mechanics. The question is, what happens to time? Can you derive a theory that's timeless? And there are many attempts at this. Of course, we don't know. There's nothing per se wrong with any of these approaches, but the problem is that we have zero consequences from any of them. We don't actually know whether they are the right thing to do or not. And in fact, these problems can occur even in classical theories. They're not necessarily quantum theories. And that's really the point that I want to make here. When people talk about the problem of time, it seems to me that quantum mechanically, this is no different to what we would call reparametrization in classical theories. And so I don't anticipate anything new here. Also, like I said, it's very hard to think of any experiments at this way. Before I do this last bit, maybe I will make a brief stop, just because I realize there could be questions, but it's very difficult for people to ask questions because I can't see the whole audience. And I think it's difficult to interrupt people. So if I make a 1 minute stop, just to allow for questions, now is maybe a good time.
Okay. Are there any questions? Sorular var mı? İngilizce soramayacak olan varsa çevirmeyi deneyebilirim arkadaşlar. Any questions so far?
Yeah, I have a one.
Who?
Zafer.
Ha, Zafer hocam. Tamam.
Okay.
Göremedim. Hocam kamerayı da açın istiyorsanız.
Nasıl? Açık.
Kamerayı da açabilirsiniz.
Kamera açık. Tamam.
Okay, we have a question from Professor Zafer Gedik from Sabancı University.
Hello, hi.
Hi, Vlatko.
Hi.
I have a short question about superposition for massive objects you mentioned. We have some examples at the molecule level, right? Like ammonia. But what about the superposition like electron, positron plus positron, electron divided by square root 2? Do we have a super selection rule? Do you think that we need super selection rules?
Excellent question. This is a really excellent question. It's a very deep question. I don't have an answer to that. I think that's again not necessarily related to gravity, but it's to do with the general failure of the superposition principle. And you are right that it could already fail in a different domain because of some other conservation principles. So I talked a lot about the equivalence principle, but you can talk, for instance, about parity conservation or charge conservation in general, and so on. And I think these very exciting superpositions that you're talking about, it seems to me that some of them get into trouble with microcausality. So, you know, the one where you're trying to, for instance, superpose even and odd numbers of electrons, there is a very beautiful argument due to Wigner that actually says if you could do that, then you could also signal at the same time. And this is one of those super selection rules that we think it holds. The one you mentioned, I can't see anything immediately obviously wrong with that, but it's never been done actually. And I think it would be great to test that as well, because you're right, you know, people always emphasize that maybe, you know, the equivalence principle will lead to collapse of superpositions and so on, but it could happen that it comes from a completely different direction actually.
Okay, thank you very much.
Thank you.
Well, I have a quick question. I never realized something. Whenever I was learning quantum theory, I never understood this simple issue. Time is an observable quantity, but we don't have an operator corresponding to that.
Yes. Yes, I think this is another very fundamental question, because the way we avoid this issue, this is really to do with the boundedness of the spectra of the energy and the time operators that you expect. And it somehow is linked to this fundamental belief that we should have a lower bound on our energy spectrum. We should not be allowing energy of a system to be as negative as possible. The reason being that it seems that then we can violate laws of thermodynamics, because we can always somehow get energy out of this very, very low energy that we have to start with. So it seems to be able to lead to some kind of perpetual machine if we allow this. And as you say, as a result, we cannot really define properly the time observable. And now the way that field theory avoids this, and like I said, when it comes to quantum gravity, it's not clear that this is the right thing to do ultimately, but field theory simply downgrades space also into a parameter. So field theory says we cannot quantize time to make it an operator like space, but what we can do is dequantize space. So actually what's quantized are the fields, but they still sit on effectively a classical background. And this could get into trouble about what I was talking about, a metric written in terms of the metric itself, G mu nu, because if you do have to quantize this G mu nu, then you should start to worry about quantizing time. And it seems to me no one really knows how to do that.
Because you see, I mean, even in the uncertainty relation case,
yes,
you usually have operators and the uncertainty relation comes from the non-commutation. But when
yes,
you go to the uncertainty between energy and time, you have Hamiltonian, but you don't have anything for time.
yes. Yes, you're absolutely right. This is an issue. In fact, I think it could be related to a host of other issues, which I think drives some of the research that Honor and I have been doing, because it seems to me that when you're talking about very small distances and very small times, it could be that because of quantum mechanics, we cannot tell whether two events are space-like or time-like. So the distances are so small that we can't tell, even in principle, actually, we cannot tell how causally related or unrelated two events could be. And this gets us into all sorts of troubles, because maybe what this means is that different components of space should also maybe not commute at some level. And I've been thinking a little bit about that. So, you know, for instance, take the electric field. We think of the electric field components as commuting, but the corresponding components of the electric and the magnetic do not commute. But actually, maybe at some very small distances, it could be that even different components of the same field no longer commute. And I think this would force us to quantize in a radically different way. It's a very deep question. And again, the frustration is that we have no experimental evidence either way what to do.
Thank you very much. So
Thank
Honor has a question.
Hi, Vlatko.
Hi.
Thank you very much for this nice talk. Actually, I have a question regarding the correlations beyond super quantum correlations. You know, Popescu and Rowley try to drive quantum correlations from two axioms, causality and non-locality, but they will end up something beyond quantum correlations.
Yes.
And you said that when we move on to the Heisenberg picture, there is nothing non-local. Do you think is it possible to discriminate quantum correlations and these super quantum correlations in the Heisenberg picture? Is it possible to say something about this?
I think this is very interesting, because my intuition would be that you could tell this through the Heisenberg operators and Heisenberg correlations. So we could phrase the whole violation of Bell's inequalities purely in terms of operators and not in terms of quantum states. And then I think the PR boxes would still be correlations that go beyond quantum correlations. But interestingly, you could account for them with local operators. But I think you would just have to change the dynamics of these operators and how they couple with one another. But I believe you could maintain completely the local description of your system. In fact, it's nice that you raised this question, because it seems to me that rather than entanglement breaking down and things becoming more classical, I think we're going to go in the direction that you are suggesting now, that things will become even more quantum and correlated, and quantum mechanics will become a special case of this in some sense.
Thanks a lot.
Thank you.
Okay, I guess we can proceed.
Yes, thank you. Let me go on this.
To
Go.
a little question about first illustration you showed about the test particle.
Yes.
Can we use a phase space, I mean Kurt phase space, to solve this problem?
Great question, and the answer is
that we can take our wave function from that.
Excellent question, because this is exactly one of those theories that would fail. And it would fail because what you're going to do with your tensor is take the expected value of your tensor with respect to a superposition of this kind. And what this means is that field theory in curved spacetime, which is a semi-classical theory, as you say, would effectively predict that there is an averaged field which emanates from an intermediate point here, and it would basically say that this test mass should accelerate in that direction. So it's very interesting that I will show you now a variant of this experiment. That's what I'm building up to, where both the test mass and the source mass are in a superposition, which actually should lead to them becoming entangled. And this is impossible to explain with field theory in curved space-time. So this experiment that I will present in a minute would be like a refutation of the semi-classical approach to gravity. And I think this approach is inconsistent, in fact.
Okay, thank you.
Thank you. It's a great question, because I think it naturally leads me to the experiment. Let me make a few very brief points here. Why is it difficult to test gravity? I think for the simple reason, as you know, that it's a weak force. And the way that an atomic physicist would put this is to say the electromagnetic coupling is simply governed by the fine structure constant, which is roughly 10 to minus 2, if you like, 1 over 137 and thereabouts. Whereas if you look at the analog gravitationally, it's actually 43 orders of magnitude smaller. It's extremely small. So, if some people have said that we will never observe gravitons, because if you excite an electron and you wait for the graviton to be emitted instead of a photon, you're going to have to wait much longer than the age of the universe. If the photon takes a nanosecond to come out, then the graviton will take 43 orders of magnitude more than that. And that's much, much, much. That's the square of the age of the universe, if you like. It's never going to happen. So you might also come across papers where people say, well, that means we're never going to be able to test quantum gravity. Gravity might be quantum, but we're never going to see any of these consequences. And I think that's not true. It's true in this particular case of spontaneous emission, but it's not true in the case that I want to show you now. So basically what people have tested are these famous cow experiments, where you send a particle at one height in Earth's gravitational field at a different height. And because now they effectively evolve, the phases evolve at different rates. So gravity, as you know, is simply the ticking of clocks at different rates corresponding to different gravitational strength. In fact, like I said, there is no gravity as far as Einstein is concerned. It's really all about the clocks and the rods being modified, if you like. And what people have done is they've looked at the basic Newtonian contribution, and this is this famous cow experiment, where the potential difference between the two, mgh times time, is simply the phase that builds up between these two. And this is now confirmed, of course, beyond any reasonable doubt. What we are close to doing, but not quite, this is still semi-classical gravity, is the first order correction due to GR. And actually our atomic clocks I said that this contribution is roughly 1 part in 10 to the 16 per meter in Earth's gravitational field. And actually, there are beautiful videos on YouTube where you look at the atomic clock and you look at the experimental physicists raising the optical table by 10 centimeters, and you can see the last 2 digits on the clock change. That's how good our atomic clocks are. They are 3 orders of magnitude better than what's required to measure this shift. Beyond doubt that this exists. But what is not beyond that, what we don't know about, is whether you can superpose a clock across 2 different heights and then get it to tick simultaneously at 2 different rates. We really don't know. All of these issues about reversibility come in. I don't want to bore you too much because if you do this fully quantum mechanically, all of these interferences are fully reversible. They're unitary transformations, and the phases behave in exactly the same way as any other phase would behave. But now the experiment I had in mind, and that's the one that Chiara and I proposed, and we had our own way of thinking about this, which is very general. And then at the same time, Sugato Bose and his colleagues had a different take on this, but basically coming up with a very, very similar experiment. And the idea now is if I have 2 masses both in a superposition, what's going to happen during the evolution in the lowest order? Again, this is an experiment that's never been done, and here is the picture. So basically, there is no other field here, no gravitational field. What you are doing is you are superposing one mass to undergo interference, another mass at the same time. This is a hugely challenging experiment, actually. And what you want is you want them to couple gravitationally. And as I explained, my view of the equivalence principle at this level is that simply each branch would follow its own equivalence principle. So, you know, it's the usual picture of quantum mechanics where the superposition is simply just a superposition of different classical realities, if you like. And in each of these branches, the usual principles hold in the same way, like energy conservation, momentum conservation, and all of that. So, but because of the different distances between these branches, the strength of their gravitational coupling will be different. And already at a very simple Newtonian level, you can see that so what I'm doing is I'm assuming that these 2 are so close that that's the only relevant phase, and I'm ignoring all the other 3 phases. I'm assuming that they are much more further apart, and I could basically make them negligible. But you can take all of this into account, really. And what's interesting is that if you start with a completely disentangled state of each of these masses in their own superposition in the interferometer, if you wait for long enough, you can actually make a maximally entangled state. So that's at the point when the phase of this kind would be exactly equal to pi. That's a maximum entanglement. And what kind of entanglement is this? If you find one of the particles in one of the arms of the interferometer, the other one would be in a superposition of its own corresponding arms of the interferometer. And if the first particle is in a different arm of the interferometer, then you again have a superposition, but it's an orthogonal one with a minus sign there. And this is what we would call a maximally entangled Bell state. So it's very interesting is that having these masses coupled to each other through a field, intermediate field, could actually result in them being maximally entangled. And the only way we can explain this is that the field through which they entangle is capable of having these non-commuting quantum degrees of freedom. Otherwise, if you keep projecting the intermediate field and you keep classicalizing it, it will never happen. So this is the reason why this field theory in curved spacetime cannot explain that. And I don't want to bore you with the Hamiltonian. I just want to make one small comment here before we conclude, and then we can have a longer discussion if you feel like it. But the account of this experiment is as causal as any other field theory. So the way you can describe this H00 is the perturbation of the gravitational field. You can write it as an operator. Actually, when I do these things, I like to call this an operator, which you would represent as A plus A dagger. A and A dagger being the creation and annihilation of gravitons, if you like. And here is the density. In this case, we have 4 different locations where a massive object exists. And what's interesting is that the propagator, this is the retarded propagator, really propagates your field from where the masses are completely at the speed of light to wherever this propagator needs to get you to compute the relevant effects. So this is as causal as Maxwell's field theory. And when you quantize it, like I said, providing you are doing this with operators, quantum operators, you will never get into trouble with any of these principles, and it's very interesting. So let me give you some numbers there, just to conclude. You know, how close are we to being able to do these 2 massive superpositions and entangle them in a purely gravitational way? One issue, of course, is to eliminate all other possible sources of decoherence. And that's the challenge. How do we know that none of these extra effects are electromagnetic in their origin? So that's one comment I want to make. The second comment that I haven't made before is that if you quantize gravity here, you also get an interesting entanglement between the masses themselves and the local gravitational field. But in this case, this entanglement, and I think I remember Carlo Rovelli liking this, the amount of entanglement is actually a function of the ratio of your mass to the Planck's mass. So it gives you a different entanglement-based interpretation, if you like, of Planck's mass. And here are the numbers to show you that actually we can find a regime where this is detectable. The mass is still some 4 orders of magnitude bigger than, smaller than Planck's mass, sorry. So we can stay below Planck's mass, interestingly enough. The distances are roughly micron in size, and the times during which you need to keep this, and that's very challenging, of course, are roughly microseconds. And if you do that and you put these numbers into the phase, you will see that you will get exactly the maximum amount of entanglement. And what's interesting is that the amount of entanglement between the masses and the underlying field is actually extremely small in this case. It's negligible and you can ignore it. The reason why I'm saying this is because you may worry that the gravitational field will cause decoherence and you won't be able to see the interference because of gravitationally induced decoherence. And my point here is that if you trust this linear regime of gravity, this will not happen. The decoherence will be too small. I think this is exactly where people like Roger Penrose and Joshi would claim that maybe gravity would collapse these superpositions. So somehow the experiment is exciting because it could discriminate collapse theories and semi-classical theories from whatever we call genuine quantum gravity, at least at this level. And I think almost any genuine approach, like string theory, loop quantum gravity, any canonical approach should agree with this prediction that there is entanglement at this level. So let me leave you with these conclusions. And rather than actually read them out to you, I will stop here and then maybe allow for more questions, because that might be the best way to conclude. Thank you very much for your attention.
We thank you, Professor Vedral, for this wonderful talk. So, are there any questions? Soru var mı? Any questions?
I have.
Thank you very much.
But Barış, may I ask?
Sure. Buyurun
Okay.
hocam.
Thank you. My question is about these ER equals EPR discussions. I'm not talking about entanglement of black holes. Do you think for just ordinary entanglement, do we need any bridge or wormhole, or what is your opinion?
That's also a very nice point, in fact, and because the field is so wide open, especially in the regime of very strong gravity, which I didn't talk about at all. So if you go into black holes, then the belief is that both gravity and quantum mechanics could be equally relevant. And the only calculations we have are again semi-classical, which I'm arguing against. They may give you the right answer to the lowest order, but they are almost certainly wrong. So, all of these Unruh effect and Hawking radiation, I'm not even sure how much I believe these conclusions, actually. They're all semi-classical. And I think the possibility you are raising is very exciting, because I come with a bias that gravity should somehow conform to quantum mechanics. But the question you are asking is, could it be that quantum correlations are in fact also geometrical in origin? Could I, by using these geometrical bridges, wormholes, could I in fact simulate quantum superpositions and entanglement? And I think that's a beautiful idea as well. This would be more geometrization, if you like, of quantum mechanics than quantization of gravity. And I think it's possible that these are the kind of ideas we may need when we are in this very strong regime. But personally, again, I'm betting kind of that the quantum mechanics has to be imposed on gravity, but we really don't know.
Thank you.
Any questions? Any other questions? So, Professor Vedral, I have a question about the things that are not written here. I mean, what is the latest situation in the experiments that you didn't write here down, but you know?
Yes, I think it's a good point. Actually, I had a lot of slides, in fact, afterwards, just in case you ask me these questions. And I think this is a good one. I think the most advanced, although probably this is not the implementation that we are going to follow here, are these molecular diffraction experiments. So you are talking about possibly approaching 100,000 atomic units as far as the mass is concerned. So the way I was putting it is I was using something like a nanogram, maybe. I was using 10 to minus 12, it could be 10 to minus 14 mass. At present, I think in those SI units, we are probably more closer to 10 to minus 21, 22. So we are almost 10 orders of magnitude away from being able to do that. So the experiments I have in mind are the Markus Arndt group, maybe in Vienna, is the best example of that, where they are sending larger and larger molecules through a diffraction grating, and then they're observing the diffraction pattern. And already there, if the mass becomes sufficiently large, you could start to think that there is some kind of gravitationally induced collapse, precisely because the field that's generated by a mass in two different places would ultimately differently affect the rest of the universe. And when these two states become different enough, become orthogonal in the quantum language, you would effectively get the collapse of these interference fringes. But it seems to me that even these experiments are still between, let's say, 5 and 10 orders of magnitude away from what I presented and what I had in mind. And it's very difficult, like I said, to even make a prediction. I suspect that there will be a limit to how far they could go, simply because of the complexity. And it seems to me that a different kind of experiment technology will be needed. So it's probably not going to be diffraction.
Okay, thank you. And how long does it take for the masses to get entangled?
Yes, so this is a good question, because it depends on this on the mass of the object. So in my experiment, in this experiment that Chiara and I proposed, we are talking about a microsecond. Of course, you know, you could say, oh, microsecond sounds very short, but in fact, if you're comparing it to all sorts of electromagnetic effects, even some vibrational effects, we could be having much, much faster timescales. You know, in some of these experiments, you're talking about picosecond, even femtosecond decoherence times. And if anything like that exists here, it will simply destroy the superposition before gravity can do anything. And you know, this is our major enemy in this case. So we have to stabilize any other noise, electromagnetic as well as vibrational. Those are the challenges, really.
Thank you very much. Bilal,
Yes, I have a question, if I can.
you can.
Okay.
If you believe you can.
Yes, I can. There, Dr. Vedral, you said at the beginning of your presentation that if a system couples to another system,
Yes.
if a system couples to another system, you said entanglement arises somehow. And something like, yes, this one.
Yes.
And I found another paper. It is Dirk Ars, a student of, I think, Konstantin Piron.
Yes.
He's come up with this conclusion at the, he's also come up with this conclusion, and he said the superposition is a problem for defining the composite system in quantum mechanics. My question is this: should we rethink of superposition deeply and clearly again? Because
yes, I think I understand the question.
yeah, and let me say again, I mean, according to your conclusion, and as I said, I mean, before, Ars also, he's come up with this conclusion. He said, let me quote it, I mean, to be
Yes,
clear.
please. Yes,
He
please.
said, if you have two experiments on a system, a physical system described by the quantum mechanics, then these two experiments cannot be separated experiments. And he said, I mean, this superposition principle in quantum mechanics become a very big problem. If you want to describe a two separate system in quantum mechanics, then it's become impossible due to the existence of superposition.
Yes, I think exactly the opposite to this. This is exactly what I'm arguing against. And I think this is a mistake that people are led to believe because they only use wave functions and they never think about observables. So quantum mechanics has states, but it also has operators. And the only thing we observe is a particular combination of states and operators, the expected value of your operator in the state, the Born rule. That's the only thing you ever see. You don't see naked states and you don't see naked operators. So what I'm arguing is that entanglement would actually be impossible if you didn't have subsystems. That's the whole point. You must be able to say which subsystem is entangled to which other subsystem, which means you can completely engineer them and target them and manipulate them separately, like two atoms in a trap. So the way that you can see this nicely, that it's completely local and there are subsystems, is when you introduce operators. That's why I was advocating what every field theorist would advocate is using the Heisenberg representation. And then you can see that if you act on one of the operators in one subsystem, you do not change any of the operators, any of the Q numbers on another subsystem. So when two systems become entangled, they still retain their identity. I think too many popular books have been written on this, and everyone is confused because of the language. But two entangled systems, they are highly correlated, exactly as Onur was suggesting. But that doesn't mean that you can't separate them and address them individually. And that's actually how we violate Bell's inequalities. That's how we know that they are strongly correlated, because we measure them completely independently before any signal can travel between these two parties. So it is completely wrong, in my view, to think that systems lose their identity when they're entangled. They have exactly the same identity. It's just that their properties, the Q numbers, become correlated, highly correlated. And I think, you know, when I talk to people who just do ordinary quantum mechanics, they are usually shocked by this. They say, why doesn't anyone tell us this? But when I talk to field theorists, they say, that's obvious. What are you telling? You're not telling us anything new. It's completely obvious. It's trivial what you're saying. And I think it is trivial. What you have to do is you have to acknowledge that your wave function is actually a field. It's an operator. It's not a state. And with this in mind, you have no problems. There's no non-locality of any kind. So I think the person you quoted and Piron and many other people I can name now are completely wrong. They're just mistaken about they're confusing one kind of non-locality with another kind of that's what I'm trying to say.
Okay, thank you very much. I have a little question, another one.
Yes.
Maybe it is irrelevant, but you just quoted a paper of what is his name? Rovelli.
Yes.
Okay, they have a theory, a loop quantum gravity, and in the theory, the Planck scale is a very fundamental conception for the theory. But I thought a little bit 2 months ago, I don't know, before, I think the Planck scale conception seems to contradict with the Heisenberg uncertainty principle. Because Heisenberg principle says us that we can measure with certainty an operator. If our operator is a position operator, then this means we can certainly measure the space, but according to their theory, it is impossible because we have an irreducible extension of the space.
Yes.
So what do you think about this point?
Yeah, it's a great point, actually. It's a great point, and again, it's a shame that I see no way how to this actually is related to a number of things what you're suggesting, and one of them is this point that I made, that when we are talking about very small distances and times, you know, even GR itself could break down at that point. What you're alluding to is that in order to measure smaller and smaller distances, you need a smaller and smaller wavelength of light. Yeah. But because the energy goes as 1 over the wavelength of light, at some point this energy will become so big that your light will in fact form a black hole. Incidentally, we don't know whether this is the case. We're kind of applying GR to a domain where it's not really been tested in any sense of the word tested. So I don't know what I would say there, but I think you are right. What this tells us is that it's not clear how to impose commutation relations on different quantities in general relativity, because it could be, unlike in the electromagnetic field says you can measure every component of the electric field to any accuracy, every component of the magnetic field to any accuracy, but together you cannot measure them. That's the uncertainty principle, just like X and P. Now, it could be that because of what you mentioned with the possibility of making a black hole, if you have high enough energy, it could be that the commutation relations are of a very different nature. And it could be that even individual components of the G mu nu can actually not be measured to a desired accuracy. And I think this was already noticed by a Russian physicist called Bronstein. He in fact wrote a paper in 1937 arguing exactly this point. He said, it seems to me that doing the Bohr and Rosenfeld analysis and taking that quantum electrodynamics analysis and applying to gravity will not work. And I think he gave exactly the argument you gave. So I would say this is wide open. We don't know how to quantize things at that level.
Thank you very much. Thank
you. There is another question. By the way, do you have time, Professor Vedral? There's
Yes.
Thank you very much. Yusuf, you can ask your question directly. Yusuf, are you here? Yeah. Okay. Yusuf's microphone is not working. Yusuf is now doing his PhD in Salzburg and also with the Vienna team.
Yes.
Doing experimental work. So this is his question. I would like to ask that which entanglement measure method would be the best for this kind of experiment?
It's an excellent question as well. I have a bias towards these entropic quantities because I think they beautifully relate to many other areas like quantum thermodynamics and so on. But entropic measures are extremely hard to get at directly in the laboratory. What will suffice, especially if you're in the regime that I was talking about, is to look at what we call linear entropy. So to trace one of the subsystems out and look at the trace of rho squared, rho being the reduced state of the other subsystem. And if you take 1 minus trace of rho squared, this will be sufficient to calculate all of these measures. It's still an extremely challenging experiment because the gate you need for this is you need 2 copies of rho and you need another qubit which is conditionally going to swap the 2 states and then to interfere. So it's still an extremely complex experiment because in addition to what I presented, you would need an extra quantum degree of freedom, which would have to interfere to give you this measure. But in my view, it's the closest to what can be done directly experimentally. I don't know if it makes any sense, my answer, but I'm happy to send you some papers as well if you drop me an email.
Yusuf, is it okay? We move on. Any other questions? Any other questions?
I would like to ask you a question. Maybe it's relevant, but yeah, when we try to quantize field, spin zero field, we use commutation relation, and we try to quantize spin-half particles field. We use anti-commutation relation, and when we try to find them in supersymmetry, we use Grassmann numbers, etc.
Yes.
So, do you think that math is enough to us to explore the physics, to understand the physics? Because always nowadays, I am trying to understand string theory nowadays, and all papers I'm reading it, I mean, all the blogs, they all complain about we cannot have an experiment to,
Yes.
The string theory is right or
Yes.
to prove it. But I mean, maybe our math is wrong, because general relativity has roots from geometry. I mean, differential geometry.
Yes.
And maybe we have to create another foundation to find a theory of everything. What do you think about this subject?
I think, yes, I think...
Just a quick note, Professor Vedral. I'm sure you have understood, but the question is spiced up with Sabine Hossenfelder style. You understood, right? I mean, the Sabine, the
Yes.
physicist, German physicist. So basically, the idea is that string theory is a bunch of mathematical machinery that will lead us nowhere, and the experiments are almost impossible to be realized, so blah, blah. But in fact, you are doing quite the opposite, so.
Yes, and like I said, I think string theorists would agree that in this very low energy regime that I'm talking about, they would agree with the conclusions that entanglement should be created. So I think that would certainly be a prediction of string theory. Of course, what you can say is, oh, but that would be a prediction of all other fully quantum approaches. So if you want to discriminate string theory from loop quantum gravity, this would not allow you to do that. But, you know, with time, as we said, you know, technology may well develop to go into higher orders. I think your question was whether it's even possible that a different kind of mathematics is needed. And for me, I am more inclined to believe that something like this will happen, like I said, that both GR and quantum physics will become special limits if you take your limits appropriately, whichever way we have to define them in the new theory, and that this new theory will somehow include both, but will go very much beyond what we are doing. Again, I can't think of, you know, I end up thinking much more about the physics of this than mathematics. But one thing I mentioned were these Q numbers as functions of Q numbers. And I know that people who are doing some kind of quantization of geometry invariably end up having to invent their own calculus in order to integrate, let's say, an operator D another operator integrate. It's even questionable what can this possibly even mean, actually. And I think people are working on this, but what frequently, maybe Sabine does have one point there, that frequently our physics community and these mathematical communities are very decoupled. We hardly ever understand each other. And it could well be that there are some very beautiful pieces of mathematics that we could be using, but we are either not aware of them or we don't think that they would be relevant in the current experiments. But I think we are getting there. You know, these are questions we should be exploring as well.
So just a quick note, the main criticism of Sabine is that the science is likely to proceed without experiments.
Yes, I understand.
Like string theory. So in that sense, what you are trying to do is quite the opposite attitude. I mean,
yes.
You are trying to go to the experiments where no one before did. I mean,
that's the idea.
So yeah, exactly. So in a way,
I think, you know,
if string theory doesn't agree with this, then string theory would have to.
You're right.
So,
that's possible too. Yes, that's possible too. Yes, I think you're right. It's lucky that at least this regime is now accessible. And like I said, this would force us to acknowledge that at least some components of the gravitational field must be quantum mechanical. I think the favorite view of field theory now, it seems to me, according to most of the practitioners, is that all field theories are really effective. They're effective descriptions which are simply valid in their own energy domain. So, you know, if you tell me that quantum gravity does not converge, my answer is I don't care, because we haven't even tested the 0th order and the 1st order, which seem completely okay to me. And going beyond is really anybody's guess at that level. So I don't think this is as big a, so I wouldn't be, what I'm trying to say is I wouldn't be blindly guided only by mathematical consistency. It doesn't seem to me to be enough with a problem like this.
Thank you very much. Any other questions? So let us thank the speaker, Professor Vedral, for this wonderful talk and taking all the questions wholeheartedly. So thank you.
Thanks very much. Thank you.
Thank you very much.
Thank you.
And I particularly thank you for taking your time in giving this talk. It was a nice event, and everybody who participated, because we started at 6 and now it's almost 7:30. So 1.5 hours, almost everybody was following. I also thank them. Next week, we will have a talk by Andrea Rapisarda. It will be on chance and democracy and of sorts. So let me still thank you again.
Thank
And if you have your final words, I mean, not final words, but final words for tonight, I would say, let us have them, and then we will say goodbye. But thank you very much, really. Professor.
Take care and enjoy your dinner. I hope I didn't delay your dinner too much.
Well, this was more important than dinner. This was more important than dinner. I mean, I'm just sorry that we took so much time. I didn't expect
Pleasure, anytime.
it to go. I also thank everybody for asking questions and participation. Thank you very much.
Thank you. Take care.
Have a good evening.
You
Take
too.
care.
Bye. Take care.
Bye bye. Thank you very much.
Bye.
Görüşürüz. Zafer Hocam çok sağ olun.
Biz teşekkür ederiz Barış, çok sağ ol.
Katkıların için çok sağ ol. Yani bir an hiç kimse soru sormayacak diye bir korktum ama neyse, buralar kaydediliyor hala, pardon.